Welcome to this explainer. Today, we're tackling a topic that Cambridge principal examiner reports flag year after year as a massive stumbling block in A-level biology. We're diving into non-cyclic photophosphorylation, specifically the roles of photosystem 1, photosystem 2, and the photolysis of water. The goal? To completely demystify this process so you can easily secure those top marks.
Okay, let's jump right in. There is a very common past paper answer that goes a little something like this. Photolysis and PSI releases electrons. Now, it sounds pretty scientific, right? It uses all the right buzzwords. But actually, it contains one tiny terminology mistake that instantly costs students crucial grade boundaries. It's a fundamental error in the biological sequence, and examiners penalize it heavily. To fix this, we can't just memorize definitions. We have to truly understand the flow of the entire system.
So, let's break down those core principles right now.
Let's start with the absolute foundation. Non-cyclic photophosphorylation is all about a highly specific one-way journey of electrons. It's literally a linear flow right through the photosystem situated in the thylakoid membrane. And the whole point of this journey? To produce two absolutely vital products, ATP and reduced NADP. You can almost think of it like a microscopic electrical circuit that powers the rest of photosynthesis.
Now here's where it gets a bit counterintuitive. The sequential process actually begins with photosystem 2, not photosystem 1. I know, scientists aren't always great at naming things in a logical order. They were named based on when they were discovered, not by their sequence in the process. Students fall into this trap all the time. But the physical journey of our electrons absolutely begins right here at PS2, where light is absorbed to excite those electrons and send them zooming down the chain.
And this brings us to a brilliantly clear causal link that examiners are just desperate for you to understand. When PS2 shoots those excited electrons down the transport chain, it's suddenly left with a massive deficit. It desperately needs replacements, and fast. That is exactly why the photolysis of water occurs. This enzyme-catalyzed splitting of water provides the exact electrons needed to perfectly replace the ones that were just lost by PS2.
So, moving further down the chain, photosystem 1 is just sitting there waiting. It receives that passed-down electron from PS2. But by the time it gets there, the electron has lost a lot of its energy. So PSI absorbs more light, giving that tired electron a second massive boost of energy. This final re-excitation is exactly what allows the electron to help form reduced NADP in the final biochemical step.
In just a moment, I'm going to share the exact examiner clue that will completely change how you interpret these questions. But first, you really needed that technical framework to make the clue completely obvious. You see, understanding the biology is only half the battle. Knowing how to strategically navigate the exam paper is the other.
Which brings us to the method mark strategy.
The crucial point here is knowing exactly how to systematically process your data and show your scientific reasoning. When you're tackling complex biological data questions, you should always use the deconstruct, solve, and evaluate framework. First, deconstruct the stimulus material. Ask yourself, what are these tables and graphs actually showing me? Second, solve systematically by applying the biological principles we just walked through. And third, evaluate the reasonableness of your answer. Does it logically fit that linear flow of non-cyclic photophosphorylation? There is a direct warning straight from the Cambridge principal examiner reports that you should never forget. Students consistently lose marks by not showing their working. Always present your working with clear notation. Because get this, even if your final calculation or concluding statement is slightly off, examiners are actively looking to award you method marks for your systematic processing. Method marks are literally your ultimate safety net in A-level biology. Let's look at the top 3 examiner warnings. We need to expose exactly where students are dropping marks. If you can avoid these 3 traps, you are automatically elevating your answers into the top bands. Trap number 1, confusing cause and effect within the electron flow, like mixing up which photosystem actually relies on photolysis. Trap number 2, neglecting proper units in data interpretation or just using sloppy terminology. And trap number 3, providing generic textbook definitions instead of applying your knowledge specifically to the experimental context provided in the question.
To avoid that devastating first trap of confusing the sequence, you need to lock this into your working memory. A great trick is to create your own memory hack using the first letters of the key terms: PSI, photolysis, and PSI. Just remember, it's PSI that loses electrons, photolysis that replaces them, and PSI that catches them later. Whatever quirky mnemonic works for you, create it and write it at the top of your page the absolute second you see a photosynthesis question.
All right, it's time to talk about crafting the perfect answer.
Let's take everything we've uncovered about electron flow, causal relationships, and examiner expectations and apply it directly to fix that flawed answer from the very beginning of this explainer. The flawed answer failed because it erroneously linked photolysis to PSI. But a perfect, top-band answer would say, photolysis of water replaces electrons specifically in PS2. See the difference? It correctly identifies the biological cause and effect. It shows the examiner you completely understand that water splits exclusively to resupply photosystem 2. That level of precision is exactly what separates an average grade from an outstanding one.
Also, whenever you are asked to evaluate experimental evidence regarding these photosystems, you should run through a mental comparative analysis checklist. Examiners report that top candidates explicitly identify both similarities and differences in the data. They use clear comparative connectives like whereas or conversely to tightly structure their arguments. And most importantly, they back up every single claim by citing specific numbers directly from the provided tables and graphs. Never ever make a claim without the data to prove it.
So you now possess a highly structured understanding of the normal pathway of non-cyclic photophosphorylation. You know exactly how the electrons flow, how water replaces them, and how to write a top-tier answer. But I want you to consider this scenario. What if an exam graph shows the ATP yield suddenly plummeting to absolutely zero, despite the plant being exposed to perfect maximum light intensity? What hidden biological variable just broke the chain?
Well, the answer actually lies in how you interpret the exact command words used in that specific question. To find out what broke the chain, join me in our next explainer where we'll uncover the hidden command word traps that cause this exact phenomenon. See you then.